Hello, this is video 3 for the experimental notes video, or unit, I should say. We're going to talk a little bit about graphing today in this video. And with this one, we want to be able to create tables and graphs. Um, Basically, we want to model what's going on in nature. And a great way of looking at models is through graphs and data tables. So there's some skills you need to be able to do. The first skill is you need to be able to identify dependent, independent, and controlled quantities. So a dependent variable is going to be what you measure. The independent is going to be what you change. And controls are what stays the same. So an example might be maybe I want to figure out if sugar makes children hyper. So in that experiment, my dependent variable would be hyperactivity. Maybe I want to measure how active the children are. The independent variable would be the amount of sugar I give them. The controls would be everything that stays the same. So I want to make sure I'm using the same group of children every time. I want to make sure they're in the same environment every time. Maybe I want to make sure their parents are watching all the time, or maybe I want to make sure that their parents are not even there. But I want to keep everything else the same. That would be an example of um, you know, using these three variables. Next thing you want to do is you want to make sure you choose appropriate quantities and units for measurement. If you're measuring time, make sure everything's in seconds. If you're measuring distances, make sure everything's in meters. Make sure all of your masses are in kilograms, things like that. Then you want to make sure you use some sort of word processing or spreadsheet program. So examples are Microsoft Excel. We're going to use a video analysis software this year called Tracker Video Analysis, or maybe Google Sheets. But you want to make sure that you're using some sort of software that helps you make graphs. Now, some skills you need to make a graph. You need to be able to plot coordinates, determine your independent and dependent variables, and then choose appropriate scales. And this is what I want to focus on real quick here, choosing appropriate scales. So, for example, let's say we're looking at an event, we want to model it, and it takes 7 seconds to complete. We want to plot that time then on the x-axis. We need to figure out what each line would be worth. And what we have here is a 20 by 20 grid. To figure this out, what you want to do is you want to take the amount of your units, wherever they are, and divide that by how many lines you have. So for this example, we have 7 seconds, and we have 20 lines. This comes out to 0.35 seconds per line. It won't always turn out that nice. You may have to do some rounding. But this one's going to turn out pretty nice. I'm not going to write out every single line here. I'm going to go every other line. But each line will still be worth 0.35 seconds. So first we have 0, and then 0.7, 1.4. We're just going up the 7's multiplication table. And there you have it. We have scaled this graph to what we need. Once you plot your data, you want to look to see if it creates some sort of relationship. And we want to be able to identify what that relationship is. So the first one is the linear function. And a linear function will have a straight line with a slope. And its general form would be y equals mx plus b. The next one here is a quadratic relationship. Forms like a parabola. You may have to go back to your math book and remember what the a, b, and c represent. One important formula that we're going to use this year is our universal uh, equation for motion. And you can see how that follows pretty nicely with the quadratic formula. The next type we have is an inverse relationship. And it can look something like this. It kind of depends on the original function, but its general form usually is m divided by x. But you could take the inverse of any function. Then we have the inverse square function. That's going to be some constant for x squared. This one looks something like this, and this is a very, very important function. This one comes up over and over again. The inverse square function applies to gravitational forces. It applies to luminosity. You know how bright lights are. It applies to electric forces. The inverse square function is one that's very, very important. The exponential function it starts over here. It's generally a raised to x. We have our logarithmic. Usually starts down here, comes up like that. It's usually some constant times log. Now, the n in this equation is the base. And generally, we use base 10. But it can be base anything, base 2, base 5, whatever you want. If it's the base e, then this becomes the natural log. We have the sinusoidal function. It's kind of an oscillatory type graph. And it can be the sine or the cosine. And then we have a power law relationship. Something like that. So those are the relationships that you need to be able to recognize. Now, another skill we need to be able to do is we need to be able to make any graph look linear. So here's what we have. We have this graph right here, some position versus time, and we can see that it's probably going to be a quadratic. So what we want to do first is we want to be able to figure out the equation for this line. So to do that, we're going to pull some data off of this. So we have a t and x. And it looks like we have t's of 0, 1, 2, 3, 4, and 5. And when we look at the x values, I know I have 0 for that one. I know I have 50 for that one. And that's the only ones I know for certain. So let's take a look at this, and let's see if we can figure out the rest of this. So using the general equation, I can see that my c is going to be 0, and my b, it looks like my b is going to be 0 as well. So I'm going to be left with a times t squared. And we need to figure out what that a is. And also, it looks like instead of y's, I'm looking at positions. I better go ahead and turn that y into an x. So, if I look at this last point, I know that when t equals 5, x equals 50. Well, if I think about that, if 5 is squared, 5 squared is 25, and 25 times 2 equals 50. So it looks like a equals 2. So when I go and start plugging 2 in for a, so 1 squared is 1 times 2, so that gives me 2. And then 2 squared is 4. 4 times 2, that's going to be 8. And then 3 squared, so 3 squared is 9. 9 times 2 is 18. 4 squared is 16. 16 times 2 is 32. And it looks like, yeah, it looks like that data fits nicely with what we see for these values here, here, here. So that looks nice. Okay, now what we want to be able to do is we want to be able to turn this into a linear relationship. And that's going to be pretty easy. Basically what you want to do is you want to obey what this equation is telling you. We want to make a new chart for t squareds. It looks kind of ugly. T squareds versus x's. So when we do that, the x's will stay the same. Now we want to go through and square all of our t's. And what we want to do is we want to go ahead and plot our positions versus our t squareds. So when we go ahead and plot these points, so we got 0, 0. We got 1, 2, so that's going to be right about there. And then we've got 4, 8. That's going to be right about there. We got 9, 18. So that's going to be right about there. We got 16, 32. So that's going to be right about there. And then we've got 25, 50. And hopefully you can see how this forms a line. So what we've done basically is we've taken a curved line and turned it into a straight line. So whenever you have some sort of weird function, if you just obey what it's telling you to do and carry out that operation and then plot that new data, it should turn it into a linear relationship for you. Well, that is it for this video.